Okay, we are back again. In the previous lecture, we have seen that participation factor, but just starting again 1 or 2 pages before that, such that our continuity will be maintained, right. So, one problem in using your right and left eigenvectors, right, individually for identifying the relationship between the states and the modes is that the elements of the eigenvectors are dependent on units and scaling associated with the state variables, right. As a solution to this problem, this we have seen in the previous lecture, a matrix called the participation matrix P, which combines the right and left eigenvectors as a measure of the association between the state variables and the modes, right. For example, suppose P1, P2, basically it is a column vector, right, and your what you call P1, P2 up to this Pn, this is equation 34. This is nothing actually, this is for my own reference, right. So, that means, just hold on, that means your Pi, it can be given as P1i, P2i up to Pni is equal to phi 1i psi i1, phi 2i psi i2 up to phi ni psi in. That means, basically it is a product of your right eigenvector and left eigenvector. This is equation 35. This one nothing, right, this is for my own reference, this is nothing. Now, where in general here phi 1i, phi 2i up to phi ni, psi i1, psi i2 up to psi in. So, for kth row, that phi ki is equal to the element on the kth row and ith column of the modal matrix phi, right. So, from that, suppose you have a phi matrix, so you can find out, suppose k is equal to 2 and I is equal to 3. So, that is phi 2 3 something like this, right, is equal to the kth entry of the right eigenvector phi I. Similarly, psi I k, the left eigenvector, the element on the ith row and kth column of the modal matrix psi, right, is equal to kth entry of the left eigenvector psi I, right. Suppose here it is k is equal to 2, I is equal to 3, it will be phi 2 3 and here it will become psi 3 2, right. Now, the element p k I, that is equal to phi k I into psi I k is termed the participation factor in general, right. It basically it will come in the matrix form, right. So, it is a measure of the relative participation of the kth state variable in the ith mode and vice versa. Since phi k I measures the activity of x k in the ith mode and psi I k weighs the contribution of this activity to the mode, the product p k I measures the net participation, right. The effect of multiplying the elements of the left and right eigenvectors is also to make p k I dimensionless, that is independent of the choice of unit, right. So, in view of the eigenvector normalization, the sum of the participation factors associated with any mode, that is sigma I is equal to 1 to n p k I, or with any state variable sigma k is equal to 1 to n p k I is equal to 1, right. That is after normalization. Later also much more we will see after your this thing, that what is your some different derivation, but meaning is same, right. So, from equation 33 we see that the participation factor p k I is actually equal to the sensitivity of the eigenvalue lambda I to the diagonal element a k k of the state variable. This we have seen, that means p k I is equal to delta lambda I upon delta a k k, this is equation 36, right. And from equation 33, that delta lambda I upon delta a k j is equal to psi I k into phi j I, but for j is equal to k, right. This is nothing and this is for my own reference. So, p k I will be delta lambda I upon delta a k k, right. So, just hold on. So, after this that participation matrix, your what you call participation matrix P I, for that example which we took earlier, that for two state variable delta omega r and delta delta we will see, but before that just one page just for small thing, after that we will find out that thing, that controllability and observability. You know this from your undergraduate control system studies. Suppose x dot is equal to x plus b u and y is equal to c x plus d u, where x is equal to phi z, right. This we have defined before. Therefore, if we put here x is equal to phi z, it will be phi z dot is equal to f I z plus b u, or and this one, this y should be is equal to this y should be is equal to x is equal to phi z. You are putting here x is equal to phi z. So, it will be c phi z plus d u, right. Therefore, this equation both sides you multiply by phi inverse. If you multiply by phi inverse both side, phi inverse both side. So, phi inverse phi identity matrix. So, this side will be z dot, right, is equal to phi inverse f I z plus phi inverse b u, right. Or this output also, thus your this thing y is equal to c phi z plus your d u, that means this one, this is nothing, this is, just hold on, this is actually nothing, it is y is equal to, we can write c dash z plus d u, right. Therefore, c dash is equal to basically your c phi from here, c dash is equal to c phi, right, plus d u. So, therefore, b dash is equal to phi inverse b, because here also b dash is equal to phi inverse b and c dash is equal to c phi, right. Therefore, the n into r matrix b dash is equal to phi inverse b is referred to as the mode controllability matrix, and the m into n matrix c dash is equal to c phi as the mode observability matrix, right. So, this one your b dash is equal to phi inverse b, it is a mode controllability matrix, and c dash is equal to c phi as the mode observability matrix. Only this much for this course, not much in detail. Now, participation factor I have taken in the next page, just hold on, right, just hold on, next page I have taken. So, the participation matrix whatever we have got for 2 into 2 matrix, phi matrix is known, psi matrix is known. Now, it is actually phi 1 1 psi 1 1, then phi 1 2 psi 2 1, easy to remember. If it is a 3 into 3 matrix, that will be phi 1 3 psi 3 1, like this, right, and here it will be phi 2 1 psi 1 2 and phi 2 2 psi 2 2. So, phi and psi matrix elements are known, just multiply your this one, your P will get 0.503 angle 6.4, 0.503 angle minus 6.4, 0.503 angle minus 6.4, here also 0.503 angle 6.4. This is a simple 2 into 2 your matrix, later we will take a 3 into 3, that is why your what you call, that is why looking at this delta omega r and delta delta, they have equal participation in terms of this, which is all are 0.503, right. Now, after this, so up to your this thing participation factor, we will come to the participation factor again, but before that one interesting thing we will try to see, that is your what will be the steady state value of your delta omega r, right. What is the steady state value? I mean it is steady state value of delta omega r, that is your delta omega r SS, right. So, for this we will go to your I think it will go to figure 39. Before coming to this, just hold on, before coming to this we will go to figure your this thing, just hold on, this figure, right. So, this is actually your figure 30, right. So, in this case, to get in this case what we have to do is, for delta v reference you take as a 0, delta v reference will take 0, right, that means this value will take as a 0 delta v reference, right, and then this delta T m will take a step input. If we take a step input, that means when you take the Laplace transform step input, it will be delta T m by S, right. Then we have to find out what is the value of delta omega r steady state value, right. These are the thing, other parameters are given, for example, this value k is given, right, and for simplicity we may neglect this one, right. If we want, we may neglect T r, because T r is very small, right. So, whenever I am going to this, only from this figure actually we will derive this, that what is your what you call that delta omega r in terms of delta T m, considering all other parameters k 1, k 2, k 3, k 4, right, k 5, k 6 all were given before, we will use the same parameter. So, this is figure 30 and page number 169, right. So, if it is so, just hold on, your this thing, this is actually, if you go to this thing actually, to forget about this thing. So, if you go to this, that delta V 1, that is your figure 30, you go to figure 30, right, and page number is 169, right. So, what you do is that your, just hold on. So, first you find out, look at this figure your 30, delta V 1 will be delta E t upon 1 plus S T r, that is your k 6 delta psi f d plus k 5 delta upon 1 plus S T r. Now, from that block diagram, delta V reference is equal to 0. I told you that figure 30, you will, when you will listen to this, you open figure 30, that we have considered say delta V reference is equal to 0. If it is so, then delta E f d will be minus k into delta V 1, right, is equal to your, that means, and delta V 1 is equal to this thing, then you substitute here. So, it will become your minus your k a delta V 1 and your what you call this delta V 1 will be k 6 delta phi psi f d plus k 5 delta and delta V 1 is k 6 delta phi f d plus k 5 delta plus 1 plus your S T r, right. Then this one, the delta psi f d, it can be, this is delta E f d and delta psi f d. Let me go to the figure once again, right, just hold on, let me go to the figure once again, then I will come back. But when you will listen to this, you will just open this one. For example, this figure, that delta, when delta E f d, this delta E f d, delta V reference is 0, this is delta V 1 and this is your k a, right. So, it is minus feedback. So, delta E f d is equal to your minus k a into delta V 1, this is delta V 1 and delta V 1 is equal to that k 6 delta psi f d plus k 5 delta into 1 upon 1 plus S T r. Now, delta psi f d, if you write, I am writing over it, the delta psi f d, right, delta psi f d will be that this side it will come k for your what you call this side delta E f d, this is delta E f d and this side minus k 4 delta into your k 3 upon this one 1 plus S T 3, right. So, same thing we are writing there, same thing we are writing, just as a block diagram, just step by step you move. Therefore, this equation we are writing that delta psi f d is equal to minus k delta V 1 minus k 4 delta into your k 3 upon 1 plus S T, because delta E f d is equal to this one minus k delta V 1, that is right. So, now if you see, if you now delta V 1, just hold on, let me think. Now, delta V 1 is given here, this delta V 1 is given here, right, k 6 delta psi f d plus k 5 delta upon 1 plus S T r, right. So, you substitute this delta V 1, this whole thing delta V 1 you substitute here, this is what has been written here minus k a into k 6 delta psi f d plus k 5 delta upon 1 plus S T r minus k 4 delta into k 3 upon 1 plus S T 3 is equal to delta psi f d, right. Next is you simplify. Now, therefore, delta psi f d can be written as minus k 3 after simplification into k 6 delta psi f d plus k 5 delta divided by 1 plus S T 3 into 1 plus S T r minus k 3 k 4 upon 1 plus S T 3 delta, right, or you can further simplification, delta psi f d will be minus k k 3 k 6 upon 1 plus s t 3 into 1 plus s t r, delta psi f d minus k k 3 k 5 upon 1 plus s t 3 into 1 plus s t r delta delta minus k 3 k 4 upon 1 plus s t 3 delta delta, right. So, once this is done, then after simplification you will get that all the delta psi f d term you bring to the left hand side. So, 1 plus k k 3 k 6 upon 1 plus s t 3 upon 1 plus s t r delta psi f d is equal to minus in bracket k k 3 k 5 upon 1 plus s t 3 into 1 plus s t r plus k 3 k 4 upon 1 plus s t 3 bracket close delta delta, right. Now, further simplification will give you this 1 plus s t 3 into 1 plus s t r plus k k 3 k 6 into delta psi f d is equal to minus in bracket k k 3 k 5 plus k 3 k 4 1 plus s t r into delta delta, right. Now, therefore, delta psi f d we can write that minus k k 3 k 5 in bracket plus k 3 k 4 into 1 plus s t r divided by bracket close divided by 1 plus s t 3 into 1 plus s t r plus k k 3 k 6 into delta delta, right. Now, you assume a is equal to whatever is there in the denominator, right, and b is equal to we assume that your a is equal to numerator, that is your k k 3 k 5 plus k 3 k 4 1 plus s t r, that is numerator, and denominator b is equal to 1 plus s t 3 1 plus s t r plus k k 3 k 5 k k 3 k 6, right. Therefore, delta psi f d can be written as minus a by b delta delta, right. Now, this one that you are what you call if we go back to your again you go back to that your what you call that figure 30 page number 169, from there you can write minus k 2 delta psi f d plus k 1 delta delta plus delta t m into 1 upon 2 h s plus k d. Just let me go through that, right. Let me go through that page your 169 here. Now, here from here you can easily make it that k 2 delta psi f d, right, k 2 delta psi f d, then here it is coming your what you call k 1 delta delta. So, it is minus here, right. So, minus k 2 delta psi f d minus k 1 delta delta plus delta t m into 1 upon 2 h s plus k d is equal to delta omega r, right. So, from this from that only we are writing that equation, right. So, from this we are writing this equation that your this one minus k 2 delta psi f d plus k 1 delta delta bracket close plus delta t m into 1 upon 2 h s plus k d is equal delta, but delta t m so far it is actually step input, later we will replace for ease of analysis, later delta t m has to be replaced delta t m upon s, because it is your step input. I have not put here delta t m by s, at the end I will put it, right. So, in this case what you call that now upon simplification, all sort of simplification, that delta omega r will become 1 upon 2 h s plus k d in bracket that k 2 upon a k 2 a upon b minus k 1 bracket close delta delta plus delta t m, and from the figure 30 again we know that delta delta is equal to omega 0 s by s into delta omega r, right. So, what we will do it that we have to substitute or replace this delta delta by omega 0 upon s delta omega r and simplify, right. So, if you do so that delta omega r will become like this 1 upon 2 h s plus k d k 2 upon a b minus k 1 delta delta plus delta t m upon 2 h s plus k d, right. So, now delta t m, that the delta omega r it is 1 upon 2 h s plus k d, this is k 2 a upon b minus k 1, and delta delta we replace upon omega 0 upon s delta omega r, right. This I told you, this delta omega should be replaced by this one plus delta t m upon 2 h s plus k d, right. That means that if you simplify this, I mean bring this delta omega r term to the left hand side and simplify, right, then what will happen, that equation can be written like this, right hand side will be delta Tm upon 2 Hs plus Kd, right. So, this one actually first what you can do is that delta Tm by S, that will replace later. First you see this S is there. So, both side you multiply your by Bs, right. So, it will be your what you call, if you multiply both side by B into S, first we have multiplied both side by S, right. So, if you multiply both side by S, so it will be 2 H square plus S K D plus omega 0, your K 1 minus K 2 A upon B, S will not be there, right, omega 0 is there. So, both side if you mark this, then this will be S into delta Tm, this is we will see later, right. Now, your what you call, now both side you multiply by B, if you do so, it will be 2 H B square plus B K D S plus omega 0 B K 1 minus K 2 A delta omega r is equal to B into delta Tm into S, right. So, that means your this delta omega r actually B delta Tm into S. Now, step input delta Tm actually now will substitute delta Tm by S, right. So, if you do so, if you substitute here, if you that numerator that is your B term is there, and delta Tm by S, and another thing is S is there. So, basically S will be cancelled and numerator it will be your simply B delta Tm. That means, let me clear it, that means your numerator will simply become your B delta Tm, right. Numerator will simply become B delta Tm, right, and multiply both side by now S. Therefore, your delta omega r steady state is equal to limit S tends to 0, your what you call S delta omega r. So, this is your nothing but delta omega r S S, right, and this side limit S tends to 0. So, this numerator S tends to 0 means it will be 0 by something. So, steady state error of delta omega r S S will be 0, right. That means, this value will be 0 for delta V reference, right. So, this is actually I tried of my own, actually book it is not given, just check one thing that your delta omega r S S will be 0, right. So, next will be again we will come to this, that your participation example, one example, then we will take the participation factor. Now, example. So, consider the following parameters. Now, H is equal to say 3.5 second, Kd damping coefficient is taken 0.0, and suppose A32 is given, I have made things simplified for you, A32 is given minus 0.1958, A33 is equal to minus 0.4229, K1 is 0.7643, K2 is 0.8649, K3 is 0.323 and K4 is 1.4187 and T3 is 2.365 second. With all these parameter, you please go back to equation 267 and please form the A matrix, right. So, if you form the A matrix, so A will be 0, this will be minus 0.1092 minus 0.1236. This is 60 hertz frequency we have taken. So, this is 376.991, this is 0, this is 0, and here it is 0 minus 0.1938 and this is your minus 0.4228, right. Now, if you try to find out the eigenvalues of this matrix, right, if you try to find out eigenvalues of this matrix, so it is lambda 1, 3 eigenvalues are there. So, one is complex conjugate pair, that is minus 0.11 plus minus j 6.41. From here we see that omega d will become 1.0 Hz. You know omega d is equal to omega n root over 1 minus xi square, and xi will be damping ratio 0.017. Based on that you can easily calculate. I did not give the calculation, but previously we have done it, right. So, and the another eigenvalue is the real eigenvalue, lambda 3 is minus 0.204, right. I do not know, maybe you will be knowing one thing, that regarding matrix, if all the eigenvalues of a matrix, right, your what you call, I mean if the matrix is a real and symmetric, then you will find eigenvalues are real, right. But If it is not, then it may be real, it may be some complex conjugate pair, right. Another thing of there, interesting property is there for matrix. Before proceeding further, suppose you have a matrix, right, and you are getting, suppose you have a 8 into 8 matrices, some matrix you have. Now you are getting eigenvalues something like it is symmetric, real symmetric matrix, right. It is a real symmetric matrix, and suppose you are getting eigenvalues of this. Suppose if one is minus 3, another is plus 3, right. If one is plus 2, another is minus 2, right. If one, suppose 8 such eigenvalues are there, if one is plus 1, another you are getting minus 1. If one is say 2.2, another you are getting minus 2.2. This may happen for some special characteristic of the matrix, right. So, if you get this kind of eigenvalues, if we plus minus pair, this way if you get the eigenvalues, right, then whenever you are trying to find the eigenvalues for control system, that is basically you are trying to find out the characteristic equation, right. And in that case, the characteristic equation is an even function. That is why eigenvalue may come like this, right. I do not know, book may be given, I do not know, but this is for some to improve our general knowledge, I am telling you this, right. So, and another real value, that lambda 3 is equal to minus 2.204. Now, that we have already shown how to find out right and left eigenvector. So, right eigenvector matrix is, you will get phi is equal to, that is 0.0169 minus j 0.0014, then 0.0169 plus j 0.0014, and this is 0.0014. Similarly, phi 21 minus 0.0988 minus j 0.9945 minus 0.0988 plus j 0.9945, because two eigenvalue complex conjugate pair is there. So, if it is a minus here, if it is a plus, if it is a minus here, if it is a plus, and last one is one real eigenvalue is there. So, it is minus 0.749, and similarly the last one 31, 32 and 33, the 0.0301 minus j 0.0015, and here it is also 0.0301 plus j 0.00. These two are complex conjugate actually, this one and this one, right, and last one is 0.6625. This is your right eigenvector matrix. Thank you very much. We will be back again.